Geometry section 1-3. We have a notes sheet here that I have always used as a handout. In recent years, I've used this as a handout, and this has stood in for the notes for students. So I did make these available. This and also the practice sheet that I'm going to reference some problems on, I did make this available in the class drive on your Google Classroom. I think you should either access that and maybe print it, or maybe just take notes like I talked about in the previous video. And also I wanted to say that we are skipping section 1-2. It's just not something that's a focus of either the Michigan Merit Curriculum or the national standards. So we do skip over that and we move right on to 1-3. And I realize again that this is not the most dynamic material, but it's a place we have to start. If we don't have words to use, then we really can't build on that foundation to move to the next level. So we're going to talk through this worksheet here, and then we'll do a few examples, and then lastly we'll go over to a practice worksheet just for a couple more, so just for some diversity in examples. So your book actually uses this language right here. It says, in geometry, some words such as point, line, and plane are undefined. In order to define these words, you need to use words that need further defining. It sounds like I'm talking in a circle, I realize, but I actually copied that right out of the book. And it says the following descriptions are very general in nature. And then we start with point. Now you may have a working definition of point. Specifically in geometry, it's defined as a location represented by a dot but having no size. A point is always named by a capital letter. So for example, when I'm teaching in class and I put a point on the board, I have to make it, from my perspective, pretty large just so that the students in the back can even see it, right? And even if I made it small, even if I just walked up with my marker and made the smallest tiny little pinprick point that I could so the students in the back couldn't even see it, even that little point has size. But really, a point is an instantaneous location. So I intentionally make it bigger so students can see it, but it's not like it's something that has area. And again, emphasis on that second part, capital letters. We'll always name points with a single capital letter. You have triangle that has 3 vertices. You might call that triangle A, B, C. That's because the vertices might have each of those names. One of the vertices is A, one of the vertices is B, one of the vertices is C. Space is the set of all points. Think 3-dimensional when you see that. A line is a series of points that extends infinitely in opposite directions. Okay, now you're either probably coming out of Algebra 1 or maybe just a pre-algebra class, and you have a certain definition of what a line is when you are graphing lines on the coordinate plane. And that's not wrong. I mean, we're not changing the definition of a line, but the perspective is changing some because we're not going to be on the coordinate plane now. But just based on that definition that we just read, you ought to agree with that, right? You drew a line, but maybe more specifically, you plotted a few points on the graph, and then you inferred where the line is going to go, right? A line is an infinite set of those points, but you don't have the time to draw infinitely many points. You could spend the rest of your life just trying to draw one line and you'd never get there because there's infinitely many points on a single line. But if you could get 2 or maybe 3 or 4, just to be sure, points out on the coordinate grid, then you were confident that you could draw your line. Well, it's the same thing here in geometry, except that line is not going to be on the coordinate plane. It might be on your paper. It might be on my board. It might be traveling through 3-dimensional space. The rest of that definition says a line can be named by any 2 points which lie on the line, such as what you see there is line AB. That's the way we would say that. You put AB, capital letters, and you put the line over the top. Okay, please do not use more than 2 letters. It's always 2 letters. And if point C were on the same line, well, then you could call it line AC, or you could call it line BC. You just need to use 2 points that are on that line. Those would all they all represent the same set of points. Okay, so it's the same line. Collinear points. Do you see the word line in collinear? These are points that lie on the same line. By the way, any 2 points will lie on the same line. The line does not have to be drawn for that line to exist. In class, I'll try to describe for you the example that I use here. I'll draw a point on my board, and then I'll step away from the board, and I'll say the other point is at the tip of my finger, and I'll hold my finger up. Well, there is a line that would pass through those 2 points. And the line does not have to be drawn on the example that you're given for us to know that that line exists. So when we talk about collinear points, we really are talking about 3 or more, because any 2 points are collinear. A plane is a flat surface that has no thickness and extends infinitely. You might think infinitely in 2 directions, right? So if you think of a sheet of paper, but then it's extended to the left and right and also extended up and down infinitely, that's what a plane actually is. Planes are named by either a single capital letter or by at least 3 of its non-collinear points. Points and lines in the same plane are coplanar. I think I'll talk a little bit more about that when we get to the practice sheet. Okay, and then lastly, we will have, as you've already seen, we have definitions in geometry. We will have postulates and theorems. Postulate, axiom, that just depends on the textbook, which one they want to use. Our textbook uses postulates. And it's simply an accepted statement of fact. When we get to theorems will be when we start to prove things, okay? So a postulate is just something that we should all agree is true. It's a starting point. It's not something that can be proved, but we'll go through these 4 right now. I think you'll agree that they're pretty obvious. So postulate 1.1 says through any 2 points there is exactly 1 line. I kind of already made that point, didn't I? Postulate 1.2 says if 2 lines intersect, then they intersect in exactly 1 point. Now, you would have experienced that in your previous class too when you were solving systems by graphing. You graph 1 line, you graph another line. The intersection point was the answer to your question about systems. Well, it's, and the geometry take on that is much the same. You got a line, you've got a different line, and they intersect. They'll intersect at exactly 1 point. This is not a situation where you draw 1 line on top of the other. That's not intersecting. Those would be actually the same line, right? So when they're different, meaning they have different slopes or whatever, I hope you know that word, they intersect at exactly 1 point. In 1.3, it says if 2 planes intersect, they intersect in exactly 1 line. If you have a couple of pieces of paper near you, it's pretty good visual to show 2 pieces of paper intersecting and the fact that they form a line. Now, more specifically, they actually form a line segment, okay? And that's because your paper is limited in size. It's probably 8.5 by 11. So if we define plane the way we just did up above, well, then your line segment that you would see when you put 2 pieces of paper together, intersecting, would actually be a line, meaning that it would go infinitely in those 2 directions. And then postulate 1.4 says through any 3 non-collinear points, there is exactly 1 plane. Here again is an example that I'll use a point in space, and I'll put two dots on my board, 2 points on my board, and then the 3rd point is out in space, and you try to imagine there's a plane that would pass through them all. And there absolutely is a unique plane that would pass through any 3 non-collinear points. Now, if you threw a 4th point in there, all bets are off. You're not guaranteed to find a plane to pass through 4, but it's for sure will pass through 3. Sometimes we use the word contain. The plane would contain those points. All right, now to some examples. This says in the figure below, name 3 points that are collinear and 3 points that are not collinear. So pretty easy to see that the 3 red ones would be collinear, Z, Y, and W. By the way, that's not line Z, Y, W. They said name 3 points that are collinear. They are Z, Y, and W. 3 points that are not collinear would be any 2 of the red ones plus X, right? So how about X, Z, and Y? Or how about X, Z, and W? Or even X, Y, and W? As a set, those 3 are not collinear, meaning they do not lie on the same line. A common misuse of the word collinear is to say the line is collinear. Well, stop and think about that. The line is collinear? Collinear means they lie on the same line. Isn't that an obvious statement? The line is collinear. That really doesn't make sense. It's points that we want to speak of when we're using the word collinear. Next example. Name the plane shown in 2 different ways. Now, I don't know that was really on the sheet if I remember, or maybe I just didn't cover it, but we want to name a plane using at least 3 letters. It did. Oh, yes, I remember now. It did say, because it said you can use 1 letter. We're going to kind of steer away from that, and I'll show you why when we get to the practice sheet. But and instead we're going to steer towards naming it with at least 3 non-collinear points. So, for example, you could say on this one RST. Plane, excuse me, I should use the word plane. Plane RST. Or you could say plane RTU. There's nothing wrong with using all of the letters either and say plane RUST or whatever. Okay? And they'll give you several examples here, including all 4. Now this example is a little limited, and that's one of the reasons why I'm going to pull in the practice sheet before we're done here. Two more examples first. It says, use the diagram below. What is the intersection of plane HGC and plane AED? Okay, now a little bit of a caution on this example, because plane HGC isn't just the back square, it's the plane that contains the back square. H, G, and C are all on the back. Would everybody agree with that? So here's H, here's G, here's C, so we're looking at that back square. But actually, because it's called plane HGC, we're not just talking about that square, but rather the plane that would extend infinitely in two directions. Okay, think of it kind of like it slices through right that very back face. Okay, and because it says plane, and we know that planes intersect in lines, then you might look at this and go, okay, HGC is the back and AED is the left side, right? AED is the left side. So it must be this segment right here. Well, that segment is the intersection of those two squares, but the intersection of those two planes would actually be the line HD. They do a good job explaining that right here. The segment HD, and this by the way, is the segment symbol. When we want to talk about points we want to talk about a set of points that are between two endpoints, those endpoints being H and D. This is the segment symbol. We already talked about the line symbol though, and that's really the answer, line HD. Because planes extend infinitely, they intersect in a line. One more, I'm not crazy about this example either, but this is the one they give me. It says shade the plane that contains X, Y, and Z. Okay, so that would be kind of the back triangle there, and I'll do the best I can to kind of shade that in. That's all. Okay, and finally then, let's just look at this practice sheet and grab a few examples. First of all, this picture right here, I want to make sure you understand the perspective. The parallelogram, that's what this shape is. What they're trying to do there is show a plane that has some depth to it, right? So this is kind of supposed to be the front, even though planes are defined as not having, edges. They have to. We're trying to draw this figure on a piece of paper. It's got to end somewhere for it to work. So in actuality, the plane would extend forward more, backward this way, infinitely forever. But this is the depth they're trying to show you in that picture. This is a line that's actually piercing it, right? So the dashed line is saying, okay, it's invisible back here, right? You can't see it because the plane would be blocking you there. And then these are two lines and a whole bunch of points that are actually lying in the plane. Okay, so here's the deal. This letter right here, Q, is the name of the plane. You could call that plane Q. Now again, I'm not crazy about that, and we'll tend towards 3 letters or more that are non-collinear, 3 points that have capital letter names, that is. But this would not be wrong. And the giveaway on this is that the Q is not near any dot. If there was a dot here, well, then maybe that's the point Q. But since it's way off in the corner, there's no point that's near it. It's obviously the name of the plane. I think a better way to name that plane would be to say plane AEC. And do please use the word plane, or plane ABD, or plane ACD, or BCD, many different combinations there. What you should not call it is plane ABC. You see, A, B, and C are collinear, and there would be many planes, infinitely many planes, that would pass through that line. Just coming in at different angles, there would be other planes that would pass through that. That's why they have to be non-collinear. Okay? That was the main point that I wanted to make about this worksheet. Let me just scan real quick. See if there's something else that I want to bring up. Let's tackle just a couple of questions in here. Are the following sets of points coplanar? The following sets of points coplanar. EBF. Absolutely. There would be a plane that would pass through E, B, and F. Even though it's not the plane that's drawn, there is a plane, as we saw in one of the postulates, that passes through any 3 points. So yes, there would be. Look at 9. Line DB and line FC. DB is in the plane here. Line FC is out here. Oh, so the line, if I can try to draw it, line FC does this. And the first line is DB is this one here. Now, does it look like those are going to intersect at all? No. Do they look parallel? You know that word parallel? We'll talk more about that later. They don't look parallel either. So those lines are going to pass each other and never intersect there. And there would not be a plane that would pass through both of those lines. I think that's a really good example. I'm glad I did those last two because that really, I think, drives home the point about those. Now, in a different lesson, we will have a word for these two lines, and it's called skew. The lines are skew. That's coming later. All right. Thank you for tuning in. Until next time.